In the previous videos, I think we left it at the concatenation method in Torch. So in this video, let's discuss that, how it does the concatenation, and then we can continue on the tensor chapter, I would say. So let's just look at an example in the PyTorch documentation itself. It's actually pretty clear here how the concatenation works. So when we want to concatenate multiple tensors, in this case we're just repeating the same tensor, we can also let's see actually, yeah, so it's an optional dimension as an integer we need to pass, and the which tells the dimension over which the tensors are concatenated, right? So if we look here, so we have x, 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 and we want to concatenate on 0 dimension. So what that means is it's just going to concatenate x multiple times. So you can see 0, 1, 0 0.6580, negative 1.0969, blah, blah, and then the second tensor here, and then you can see after that it just the whole tensor is repeating, right? So that's because we are doing concatenation on 0 dimension. So if we do it on the first dimension, that means let's look at what that means, right? So if you look here, we have 0, -1, 0.46, and then we have 0.65, -1, 0.4, negative 0.4, 0.65. So as you can see, instead of repeating the second tensor, it's actually, because we asked to do concatenate on the first dimension, it's gone in and concatenated the whole tensor into one. So as you can see, the length of this tensor versus the tensor length here, you can see that the items are being repeated from here onwards, right? So that's basically how the concatenation works, and you can also define provide the dimension to control that, and that's quite powerful actually. If you need to write the method manually to do this kind of operation, that's a lot of code, and also you gotta think through a lot. So PyTorch provides that out of the box. It's really handy. I would still encourage you to try this on your own and just get a full grasp, because yeah, it first, in a first glance I thought I understood it, but then when I really start to look into it, and then yeah, that, which is why I had to pause the last video, stop the last video, and then redo it. Now then we have the arithmetic operations section. So if we go back to tensors chapter in the Python PyTorch documentation, which is this, for some reason if you don't have it. So it's on the introduction to PyTorch and tensors. So arithmetic operation. Now what we have here is this computes the matrix multiplication between two tensors. So y1 and y3 will have the same value. Tensor.t returns the transpose of a tensor. So here what we're basically doing is we're multiplying, sorry, these links that take me to the tensor documents there. So multiplying a tensor by a transposed tensor. So let's just look at the code, what that means, right? So if we look at I'll just do escape command B there. That gives me a new prompt. So if I just look at a tensor, I think I should just run this all, so that just saves time. So you can just skip the video for it. So here, if we look at, interesting. Why did it fail? Run all. Yes, I'm not going to cut this video or edit it, so please skip the video up to wherever you like. So what's the problem here? So the problem is the code there, and that should be fine. So let's look at a tensor here, and then I mean that doesn't really need an execution. So that's the tensor we have. But when we do tensor.t, we get a transposed tensor, and let's see what that looks like. In fact, let's just do that on another cell so we can still compare. I'll just get rid of that t there. Okay, so what did really change here? You can see the dimension. So when I guess the simple way I can show you is on Google Sheet. If you copy this and then you can do paste special, edit, paste special, transpose. That's what it does, right? So it went from rows to columns, or you can say from like a so this is on one tensor versus this is on multiple tensor, right? So if we look at the tensor scenario, so this would have been one tensor in a sequence, where this is like the 0th index of the first tensor, 0th index of the second, and 0th of the third tensor, right? So now let's go back, and you can see that pattern here, 0.96. So it's transposed that way, that tensor in another dimension, right? So we did that to get to see how the matrix multiplication works basically, right? So instead of creating another tensor, now let's just look at. I found this really detailed matrix multiplication. What do I say? Like not tutorial, lesson on mathisfun.com. So you can go and check this out. I'll leave a link in the description. And you can see here a matrix is an array of numbers, and that's just a matrix which we already have. To multiply a matrix by a single number is easy. So you multiply that, each element of that matrix with the number that you want to multiply, and this number is called scalar. So you multiply 4 by 2, you get 8, 2 by 0, 0, 2 by 1, 2, 2 by -9, -18, and that's your matrix multiplication done. Now, what we are doing over in PyTorch is multiplying a matrix by another matrix. So as you can see here, what we are doing is we are basically multiplying 1 multiplied by 7, 2 by 9, 3 by 11, and then we get the result 58, which is the first result for the first index of the next, the result, the matrix that we're getting the output of, right? So, and if we keep going down, we can see here the second as well. So we're doing the same multiplication with 1 by 8, 2 by 10, and 3 by 12, and we got 64. So we're following that, and what we get at the end is 58, 64, 139, and 154. That's how the matrix multiplication work. And I will encourage you to read this, why do it this way, and what is the rationale behind it. And they've given a really simple example here of a sales record, and how they calculate using matrix multiplication, and how it comes in handy, right? So please go ahead and read that, and then let's go back and we look at here. So to do all that in PyTorch, all you have to do is have two tensors, and this @ symbol does the matrix multiplication, and that's it. Like, it does all that for you, right? So that's very handy. And then if we look at the next option here, so we can just look at y1. So y1 is the result of the tensor multiplied with this tensor over here, right? And now to move to this matmul, we'll just check here in the documentation. tensors. So go back to the documentation. So what does the matmul do, right? This computes the element-wise product. Tensor returns transpose of a tensor. Then y2 matmul with. So that's a basically matmul is the matrix multiplication method instead of this operator, right? So you can do either or to get that result. Which one is a method and one is a operator. So I'm not too sure if there's a difference here. I don't want to dive in deeper into this, but for me, I think it just one you can do using the operator and another just using the method. And so you're defining, like, you're multiplying this tensor here with the second tensor t, which is the transpose tensor we talked about. And after that, what do we have here? So we got torch.rand like, and so we got the random like the first y1 tensor, and then we're doing the matrix multiplication again here. Nothing new here, but I think what's new here is the out equals to y3. So what we're doing here basically is, I think I read that in the documentation here. Let me just go to. So out is the tensor, the output tensor. So basically when this operation is completed, this matmul operation, the result will be stored in, result will be stored, referenced by y3, right? So that's the reference to where the result is stored in the memory, basically. And then we have here, this computes element-wise product. Z1, Z2, Z3 will have the same value. So this is a simple multiplication, matrix multiplication. Tensor, this computes the element-wise product. Z1, Z2, Z3 will have the same value. Okay, so let's just try this out because I'm not 100% sure what that means. Okay, so I'm just gonna run this and then run that. So here I understand they have the same result, but how do I, so let's just get tensor 1 is torch dot tensor, and then we just say 2, 2, 3, and then we'll just do another one here, 4, 5, right? And then we have next one, T2 torch dot tensor. For this one, we'll just do 1, 2, and then we'll do 3, 3. Okay. So I think I need to opening for this one here, and then yeah, that should do it. Now let's just do this multiplication they're referencing here in the doc, which is just doing tensor multiplied by tensor. So what do we get? T1. So we'll just print T1 and then T2, and then we'll also print T1 multiplied by T2. So what's the result and what it does? So 2, 3, 1, 2, 3, 3, and it does exactly what I thought it does. So 2 by 1, 2, 3 by 2, 6, 4 by 3, 12, 5 by 3, 15. So all it does, I mean, the thing is, I sort of guessed what it does, but I don't want to leave this video on guesses. I just want to, first of all, for myself and also for you, for anyone who's watching, I want to clarify, like I want to see it in the screen. So basically, if we go back to this here, so this computes element-wise product, right? So it just goes in each, multiplies each matching indexes on the matrix and then gives you the output. Single element tensor, if you have one element tensor, for example, aggregating all values of tensor into one value, you can convert it into a Python numerical value using item. So AGG, so tensor.sum, and then we can do aggregate.item to get the actual value. So let's just see it in action again here. So if we just do sum is t1.sum, so that sums up all the values within that matrix, and then if we just do sum.item, that gives us the sum, the value of sum, right? So what's interesting is, let's just check what's in the sum. So if we just print sum, okay, sum is like a tensor, has 14 as one value there, and so when we do item, it just gives us the value by itself without having this tensor type. Okay, that makes sense. Let's go back to the doc and in place operation. So operations that store the result into the operand are called in place operation. So what that basically means is if we do 2 multiplied by 2, so that's 4, but at the moment we have no way of referencing that 4, right? So what we usually do is we do a equals to 2 and then b equals to 2. Let's just do another number for just clarity. And if we do a multiplied by b, we still have no way of referencing that result, but we have we still have the reference to the number that created the new number, right? So we still have a and b, what I'm trying to say. And then what we can do is c equals to a multiplied by b. And then now we have reference to all values, including the result. So we know what a and b are, and we know what the value c is. Now what it's trying to say here is operation that store the result into operand called in place, right? So they're denoted by the a suffix. For example, x.copy underscore y. So what it does is it replaces x with this copy of this y. So even if you change y, it won't be reflected in x. X will have a copy of y that is independent, and x references to this new location in the memory. And then same thing here, x t underscore, so what's t here? For example, copy, so it's transpose, so it will transpose into its own yeah, let's just check what that method does. Let's just do a quick Google search. So it's same transpose, which I guessed. Now, but if you do the t with the underscore, it will just transpose it and then replace x with that new transposed value, right? And you may end up doing these type of operation to be a little bit memory efficient, and you basically don't leave the the x's in this case, or the alt values in the memory, just for them to just store there, right? Because in some cases, like in many cases, the matrices you're dealing with can be very large and they take significant amount of memory. So I hope like you understood that, and that was a very long-winded way of getting about to understand it. But yeah, I think it's still worth it. So in-place operations save some memory. So there we go. But can be problematic when computing derivatives because of an immediate loss of history. Hence, their use is discouraged. Okay. Yeah. So what it basically means is you no longer have the previous values, and if you need to come back and reference the previous values, you won't be able to reference them, right? So what the documentation is trying to say is just like you need to fully understand it to be able to use it. So there will be times where you want to use it, in very static cases, I'm saying, but I'm guessing, but in most cases you probably don't want to do this, because when you run neural network like forward pass and back propagation, like you need to be able to calculate derivatives, and you need to be able to like know how you get to the number and how can you go back into the previous numbers, right? So that's what the documentation is saying here. Bridge with NumPy. So I think this chapter is just this section of the chapter is just trying to explain how you can go back from NumPy array to Torch, and Torch to NumPy, and we did discuss that a little bit in the first video, but let's just quickly look at it. So you can do torch.ones, that gives you tensor of ones with 5 element, and then if you do t.numpy, that gives you the NumPy array, right? So what does that mean? Basically what it means is like, so for example, if we go back to our documentation here, if if there is a specific operation that NumPy offers and you don't have that in Torch, you will be able to use that, right? So it's the data type that NumPy it will be the type that NumPy uses. So for example, tensor here, if we look at the type of a tensor, it's torch.tensor, right? And then if we do type of, I'm just going to do it on the same .numpy, and then it's a method, I think. So that's the type and NumPy array, right? ND array, and so the difference is now. Let me just read on this. Yeah, so if you have a method that Torch provides, you need to have this type of object in the memory, and if you want to use the method that NumPy provides, and for let's just imagine for whatever reason it's not in Torch, you can just use the second one. So you want to easily go back to NumPy and then revert back from NumPy to Torch, where if you need to go back to Torch. So that's the bridge that this section is talking about. And let's just go back to the documentation here. And what else is there? A change in the tensor reflects in the NumPy array, right? So for example, what it's saying here is t add 1 and t. Okay, so let's just try this. So what it's trying to say is, if we do, let's just do here the next cell, a equals to so we have a tensor, and I'll just do a equals to tensor dot numpy, and then I'm just going to print tensor and also print a, and then so we have that. It's just a copy, and then what I can do is in one of the tensor I can just do I actually don't know the method what they did here. Let's just look at an example. So add one changes. Okay, so that will just go and add one to everything. So just to add one, so we're changing on that tensor. And now if I go and print this again, both of the outputs should reflect the same result, right? Just like how they are now. There we go. So we added one, and that is reflecting on everything at the moment. And why that is it's because I have a separate video on Python basics tutorial about this. It's because they reference the same matrices in the memory, right? So when you do .numpy, it's not making a copy of that and giving you the new object and creating a new like a space in memory and putting the copy of that space in the memory. It just has that one matrix in one location of this memory, and it just like NumPy and Tensor Torch are reading that same from that same location and giving you these different set of things to like perform. It could be different method or whatever you're doing. So right, so that's what they're trying to make it clear on this bridge section of the documentation. And then we have here numpy array to tensor, so it's same thing again, like torch dot from numpy, and then if you pass in the numpy array, it reverses everything. So I think we've gone in a decent length of the video. I'll say, yeah, leave a comment if you have any questions or anything. So I'm not sure if you watched the first video. The whole idea of these videos are like, I'm not teaching you NumPy or like PyTorch. I'm actually learning PyTorch, and I find that it's better to learn when I'm explaining things that I've learned. And then I find that I don't get things like just left out in between. So for example, like when I'm explaining something, I need to fully understand it. So which is the basically the intention behind these videos. So if you find me just babbling about something that doesn't make sense, please feel free to comment and point me to the right direction. Or if you're learning from these videos, or if you're following along, then please, yeah, feel free to comment and say hello. Yeah, I'll see you on the next video.